As you'll recall from a previous video, we've said that the eccentricity of a conic section is the distance PF divided by the distance PL, where PF is the distance from a point on the curve to the focus, and we call that R, and PL is the distance from the point on the curve to the directrix, and that has a value of d minus r cosine of theta. By clearing the fraction, we were able to say that r was equal to e times the quantity of d minus r times the cosine of theta. And before, what we did was we took that equation and we turned it into r is equal to ed divided by 1 plus e times the cosine of theta. We're going to take this equation, r equals e times the quantity of d minus r cosine theta, and go a different direction with it. First, we're going to square both sides. R squared is equal to e squared times d minus r cosine of theta, the quantity squared. And then because we're after something different this time, we're going to convert this into rectangular coordinates, and we get x squared plus y squared is equal to e squared times the quantity of d minus x squared. By simplifying on the right hand side, we get x squared plus y squared is equal to e squared d squared minus 2e squared dx plus e squared x squared. What I'd like to do is take this equation and turn it into a rectangular form of a conic section. So for that, I'm going to gather all of the x's and y's to the same side. Combining the terms that contain x squared gives us 1 minus e squared x squared. Adding 2e squared dx to both sides, we get plus 2e squared dx plus y squared is equal to e squared d squared. And just to bring in some colors here, blue for the coefficients of x squared, and then the 2e squared dx we added to the other side. Now, in order to get this to look like the equation of a conic section, I'd like to complete the square on x, and then we'll be able to analyze the equation a little bit better. First thing we got to do there is divide by 1 minus e squared. When we do that, we get x squared plus 2e squared d divided by 1 minus e to the e squared times x plus y squared over 1 minus e squared is equal to e squared d squared divided by 1 minus e squared. To complete the square, I need to cut the linear coefficient of x by 2 and then square the result. So we have e squared d divided by 1 minus e squared, the quantity squared. I'm going to add that to both sides. On the right hand side, I'll go ahead and distribute that exponent, e to the 4th d squared divided by the quantity of 1 minus e squared. We're then able to factor what's on the left hand side, x plus e squared d divided by 1 minus e squared, the quantity squared, plus y squared over 1 minus e squared. And on the right hand side, we're going to get common denominators. So we're going to multiply numerator and denominator of the first term by 1 minus e squared. And I see I missed a squared down here in the denominator under e to the 4th d squared. That was the square of the denominator as well. Now, multiplying the numerator and denominator by 1 minus e squared, in the numerator, and I sometimes do this, write little notes to myself so I don't have to write the whole thing again. In the numerator, we get e squared d squared minus e to the 4th d squared plus e to the 4th d squared. And then we're all over the common denominator. E to the 4th d squared subtracts out. We're left with e squared d divided by 1 minus e squared, the quantity squared. And that's e squared d squared, isn't it? We're almost done, folks. We just want to turn what's on the right-hand side into 1 by dividing. It may not look pretty. X plus e squared d divided by 1 minus e squared, the quantity squared, divided by ed over 1 minus e squared, the quantity squared, plus. After simplifying, and you can double check this, y squared over e squared d squared divided by 1 minus e squared is equal to 1. Here's the point of all this, folks. This is the equation of a conic section in rectangular coordinates. We can point out that the center is negative e squared d over 1 minus e squared, 0, because y squared is the sole term in its numerator. I'm less concerned about that than I am with what a is. Before we get to a, though, let's back up a bit. Here when we had 1 minus e squared times x squared, let's note that if e were equal to 1, we would zero out the x squared term and we have a parabola. Looking at our final form here, in the denominator of y squared, we have the expression 1 minus e squared. If e is less than 1, then both our x squared term and our y squared term will be positive, and we have an ellipse. If e is greater than 1, then the denominator of y squared, 1 minus e squared, would go negative. The y squared term would go negative. We'd have a hyperbola. So now going back to the idea of we want to know what a is, we started out saying we were going to be looking at orbits. And as we know, orbits are in the shape of ellipses. So e is less than 1, and that means that the denominator under the x term is larger than the denominator under the y term. Therefore, a is ed divided by 1 minus e squared. It also follows that b is equal to ed divided by the square root of 1 minus e squared, but I'm not really concerned with b at the moment. Since a is ed over 1 minus e squared, ed is equal to a times the quantity of 1 minus e squared. Now folks, I know this was a long ride, but that was this right here, what we just wrote down. Ed is a times the quantity of 1 minus e squared. That was the point of the whole exercise here. Because if r is equal to ed divided by 1 plus e times the cosine of theta, then we can rewrite that as r is equal to a times the quantity of 1 minus e squared divided by 1 plus e times the cosine of theta. This doesn't seem like a groundbreaking result here, but let's consider if theta is equal to 0, then the cosine of theta is equal to 1, and we have that r is equal to a times the quantity of 1 minus e squared divided by 1 plus e, which means that r is equal to a times the quantity of 1 minus e by factoring and dividing. If theta is equal to pi, then we have r is equal to a times the quantity of 1 minus e squared divided by 1 minus e, because the cosine of pi is -1, which means that r is equal to a times the quantity of 1 plus e. Since orbits are in the shape of an ellipse and the body that the thing is orbiting is at one focus, we now have expressions that tell us the distance when the object is closest to the thing it's orbiting. That's going to be a times the quantity of 1 minus e, and the distance when the object is farthest from what it's orbiting, and that's going to be a times the quantity of 1 plus e. In the case of a planet orbiting the sun, a times the quantity of 1 minus e is called the perihelion distance. And the farthest it gets from the sun is called the aphelion distance. Now I know this has been a long ride, but we're going to go through a quick example here. We're going to find the polar equation for the orbit of Jupiter. The orbit has an eccentricity of 0.048, so quite circular. The length of the major axis is 1.56 times 10 to the 9 kilometers. A is the length of the semi-major axis, so half of 1.56 times 10 to the 9, 0.78 times 10 to the 9 kilometers. With an eccentricity of 0.048, we can use the equation that we boxed above. R equals a times the quantity of 1 minus e squared divided by 1 plus e times the cosine of theta. By putting the numbers in that we have, we're going to get r is equal to 0.78 times 10 to the 9th times the quantity of 1 minus 0.048 squared divided by 1 plus 0.048 cosine of theta. Simplifying gives us r equals 7.78 times 10 to the 8th. I went ahead and put that back into scientific notation. Divided by 1 plus 0.048 times the cosine of theta, the equation for the orbit of Jupiter.